Okay, so good morning. Let's continue our discussion on binary distillation today. So in the previous two lectures, we basically went over the structure of binary distillation column. And we talk about the distillation column is like you bring together so it's made of like three kind of like components. So you have the rectifying section that functions like an absorber, and you have a stripping section that functions like a stripper, and then you have the feed function as a single stage flash process. Okay, so then your feed will provide a vapor and liquid into the column. Then in the rectifying section, the liquid will be supplied by the condenser, and the downcoming liquid will strip the heavy K component from the upcoming vapor. Okay, and whereas in the stripping section, the reboiler will supply vapor, and the upcoming vapor will strip the light K component from the downcoming liquid. Okay, then we will be able to produce a distillate and a bottom that is rich and depleted with the light K component. And we derived the operating lines and the Q lines for a distillation column based on mass balance, mole balance. And we also discussed basically the slope of the Q line is dependent on the feed condition, right? Depending on if it's a liquid or vapor or mixture of liquid and vapor, and then the Q line will have different slopes. Then we put everything together onto a XY diagram. We have two operating lines intersect with the Q line at a single point. Okay, then we can determine the number of stages as well as the optimal stage position by basically doing the step off process we've learned in the absorber and the stripper. Okay, so today let's look at some examples. Okay, the first example is distillation of a mixture of benzene and toluene. So here we have 450 pound mole per hour of mixture of benzene and toluene, right? In this case, benzene is a light K, and they are to be separated into a liquid distillate, right? That is reached with benzene, and a liquid bottom that's reached with toluene, right? With 95 and 5% of benzene respectively. So the feed enters a column with a mole percent vaporization equal to the distillate to feed ratio. Okay, pay attention here. So we have a feed, right? We don't know its state yet, but it's going to be vaporized, right? According to this statement, partially vaporized, which means the feed will be like a mixture of liquid and vapor. Okay, so then the problem asks us to compute the minimum number of stages, the minimum reflux number of stages if we apply a reflux ratio that's 1.3 times of the minimum reflux ratio, and the optimal feed stage location. And lastly, we need to compare the results with those obtained from a process simulator. Okay. Now let's look at what this problem asks to. First, for the minimum number of stages, right? And we've talked about this in our last lecture. So when we have a system of total reflux, that means we basically return all the liquids from the condenser back to the column. And then we have a maximum amount of liquid coming back to the column. Then we need a minimum number of stages. And in this case, the operating lines for the rectifying and stripping sections are overlapping with the 45-degree line, right? And we can just do a step-off process, and between the equilibrium line and the 45-degree line, we can find out the minimum number of stages, right? Starting from the distillate composition, which is 95% light K, and at the bottom composition, which is 5% of the light K. Okay, so then the second question asks us to get the minimum reflux ratio. Okay, so for the minimum reflux ratio scenario, we are kind of operating the distillation column. Basically, in this case, basically, the operating lines and Q line, they intercept at a point that sits on the equilibrium line. Okay. So in order to find R minimum, we need to find out where is this point, right? From the fate condition, right? It's a mixture of a vapor and liquid. We can figure out the Q line, right? We can figure out the Q line. Then we can find the intercept of the Q line with the equilibrium line. Then if we connect that point with the with the distillate point, right, which is 95%, that gives us the operating line for the rectifying section. Then we can get the reflux ratio. Okay, and for the number of equilibrium stages and for R over R mean to be 1.3. I mean, once we get R mean, we can get R, right? And we can draw the then that will give us the slope for the rectifying section operating line. We can draw that line on the XY diagram. Then we can do the step-off process, and we can find out the number of equilibrium stages and the optimal fate stage location. Okay, so that's just like conceptually, when you read this problem statement, you need to have an idea what you can do, what you should do in order to get the solution of this problem before you actually do the analysis. Okay, so here, in order to find out the R minimum, we need to get the Q line, right? And we need to get the Q line. In order to get the Q line, we need to know the fate composition, which is already known, and we also need to get the slope of the Q line, which depends on Q, right? So by definition, Q is the ratio of the flow rate change in the liquid stream, right, over the total fate flow rate, right? In this particular case, we have a fate to be a vapor-liquid mixture. So then Q is basically the liquid flow rate in the fate over the total flow rate, right? We just need to compute LF, then we can find the Q. Okay, and then in order to get LF, we can come back to this statement. It says the fate is enters the column with a molar percent vaporization equal to the distillate to fate ratio, right? So then we need to get the distillate to fate ratio in order to get to the how much vapor and how much liquid does the fate contains, right? Okay, to get the distillate to fate ratio, so once we get a Q, we can get the Q line, right? And then once we get a Q, we can calculate the slope of the Q line here. So to get the distillate to fate ratio, we can use mole balance, right? Overall mole balance between the feed and distillate on the bottom. Also the light K mole balance between the feed, the distillate, and the bottom, right? So here we know F, we know ZF, we know XD and XB. We can compute D and B. We have two equations. We have two unknowns. We can calculate D and B. Okay, so just plug in the numbers into these two equations. So this is the mass balance for the light K, then this is mass balance for the overall mass balance and mole balance for the for the total for the feed, right? And then from these two equations, we can solve for D and B. Then we can compute the distillate to fate ratio, which is 0.611. Then we have the we can find an operating line, the Q line. So since the vaporization percentage, right, that's VF over F, is the same as distillate to feed ratio, that's 0.611, and we can compute the ratio of the liquid in the feed over the feed. That's basically 1 minus vapor in the feed over F, right? That give us 1 minus this point, this number, that give us 0.389. Then we can compute the slope of Q line, which is Q over Q minus 1, right? Look at this equation here. Give us a minus 0.637, right? So this is a straight line with a negative slope. Okay. Now with that, we can go ahead and find out the number of minimal stages and the number of the minimum reflux ratio, right? Let's first look at the minimal number of stages. So in this case, the operating lines are overlapping with the 45-degree line, right? So we can just do the step off to figure out the number of stages, starting from the distillate composition, which is 95% of the light K, right? We'll start from that point on the 45-degree line. Okay. So the reason we can start from that 45-degree line is that if we use a total condenser, right, and we return the condensed vapor back to the column, so think of the stage 1, right? Above stage 1, we have a vapor phase leaving the stage 1, and we also have a liquid phase entering stage 1, coming down and entering stage 1. They have the same composition because we have a total condenser, right? And this composition is the same as the distillate mole fraction. Okay, and we do the step off, and then we find out after the 7th stage, we will obtain a composition here that is lower than XB, right? XB is the mole fraction of the bottom. So that means we need at least 7 stages, right? If we are taking an integer number of stages, if we can do a fraction number of stages, then that will be 6.7, right? So basically, we can get XB at this particular point. Okay. So then for minimal reflux, first we can draw the Q line, right? To do that, then first we identify where is the feed composition, which is 60% of the benzene, right? So you draw a vertical line that crosses with the 45-degree line. That point is at the starting point of your Q line, right? Then our Q line, we know that for the Q line, the ratio, the slope of Q line is minus 6.637. So we can draw a straight line starting from that point with a slope of minus 0.637, right? And that Q line will cross with the equilibrium curve, right? And we find out this intercept point. And we know at minimal reflux, the operating line will also cross this point, right? So then we can just connect this point with this distillate point. That gives us basically the operating line for the rectifying section under minimal reflux. We can measure the slope of this line. Then, if we plug in this equation, the slope of this line is a function of a reflux ratio, right? So you can compute the minimum reflux ratio. That's 1.22. Okay. Now let's move on to the third question of this problem, which asks us to figure out the number of stages and the optimal feed stage location if we have a actual reflux ratio that's 1.3 times of the minimum, and that gives us 1.59. And then we can compute the slope of the operating line, right? That's R over R plus 1. Plug in the numbers, you get 0.614. Then you can plot a straight line starting from the feed. This is distillate composition, right? With a slope of 0.614. You get a straight line. That straight line will cross the Q line at this point, right? Then that give you the operating line for the rectifying section. Then we need to draw the we need to draw the operating line for the stripping section, which is also a straight line, and we can just draw that line by connecting this point with this point. Now that point is basically the the composition of your bottom, right? Which is 5% sitting on the 45-degree line. Okay. So then we can just connect these 2 points. You get the basically the operating line for the stripping section. Then you can do the step off, right? Starting from point A. Then you have stage 1, 2, 3, 4, 5, 6. Then at stage 7, as we can see, that stage 7, when you draw the horizontal line, it passes this intercept point. That means after this stage, we need to switch our operating lines from the rectifying section to the stripping section. And we can continue to do this step off, right, down and much horizontally. You do this until eventually you have at a stage stage 14, the horizontal line cross the the bottom composition, right? I give you a total number of stages of 13.2. Okay, then you can compute the kind of the stage efficiency. So not a stage efficiency, the actual the total number of stages in this case for a reflux ratio of 1.3 R mean, compared to the minimum number of stages, that's roughly twice. Okay. Now we can compare the result with we obtained with McCabe-Thiele method with process simulator. This is from your textbook. So this is our kind of like analysis result based on McCabe-Thiele method. So we need a total number of stages 13.2, and our fate stage is at stage 7, right? Here, and we can get 95% in the distillate and 5% in the bottom, right? In the process simulator, so you're going to input the number of stages and the fate location, and it will give you the distillate composition and the bottom composition, right? As we can see, right? If you input an integer number of stages, it gives you a distillate and bottom composition that's very close to our design target, right? And if you, but this is still this distillate composition is still lower than our desired outcome, and the bottom composition is still higher than our desired outcome. So we can increase the number of stages, right, to 14 stages. Then adjust the fate stage location. Then we can get exact composition that match with our design, our desired separation outcome. Okay. Next, I want to introduce and discuss the concept of partial reboiler and partial condensers. Okay, so when we describe our distillation column, right, we have condensers at the top, and we have a reboiler at the bottom. And there are two types of condensers and two types of reboilers. So in the reboiler, basically, we have this liquid entering your reboiler. Then this reboiler will basically heat this liquid up and produce vapor. Okay, and depending on how much this liquid is vaporized, you can have a partial reboiler or total reboiler. If all the liquid is boiled up and become vapor, then you have a total reboiler. in this case, your this is boil up vapor, and your bottom will be both vapor, but they have the same composition, right? Because they are both vapor, and they have the same composition. YB equals XB and equals X, and that's the composition of the liquid feed, right? But if you do not vaporize all the liquid, so you only vaporize a part of it, right, then you will create a vapor liquid mixture that's in equilibrium, okay? And the vapor will be fed back into the tower, right? That's your boil up. Whereas your liquid here will be discharged out from the distillation column and become the bottom, right? In this case, XB is a liquid and V bar is a vapor, so they are in equilibrium with each other. So YB is different from XB, right? Because they are basically, they corresponds to the vapor composition, the liquid composition. They corresponds to the composition of a vapor and the liquid phase that are in equilibrium with each other, right? So YB and XB are not necessarily the same, and they also are not necessarily the same as XN, right? And typically, XN is in between YB and XB, right? So in this case, as you can see here, well, if we only partially vaporize this liquid, then we're going to create a vapor and a liquid that has different compositions, and that functions like another equilibrium stage, right? And this case, it's very common. So let's look at the difference of a total reboiler and a partial reboiler on the XY diagram. Okay. For a total reboiler, and this is the end stage, right? That's the bottom stage here in your distillation column. So at this point, right, this is the stage N cross. Well, let's look at this point first. This point is on the operating line. So that it gave us the vapor and liquid composition above stage N, right? That basically gave us the composition here. Then, so we can get YN, right, from this point. Then we draw a horizontal line that crosses with the equilibrium curve, and we have one point here. This point, basically, it's on the equilibrium line. It gave us the composition of the vapor leaving the stage N and the liquid leaving the stage N, right? And they are in equilibrium with each other, right? So we have Xn. From that point, you can read off the composition Xn here. Okay, so then we have Xn, that Xn enters this reboiler. In this case, it's a total reboiler. So then we have XB equals YB equals Xn. So you can, from that point, so that point gives you the kind of composition of the reboiler. And so you have the vapor composition, right, equals the liquid composition and equals the feed for the reboiler composition, right? That's for your total reboiler. Okay. So in this case, as we can see that operating line will cross a point now has a higher mole fraction than the reboiler. Okay. So in this case, you can achieve your desired separation outcome, but you don't really fully utilize the capacity of your distillation column. Ideally, this point overlaps with this point. Then you can achieve maximize utilization of your distillation column. For a partial reboiler, okay, we have stage N here. Then at stage N, we have YN and XN, right? YN and XN. They are basically the composition of the vapor and liquid stream leaving stage N. So we draw a vertical line down. It's going to cross the operating line, okay? Because in this case, we're using a partial reboiler. Okay, so we are using a partial reboiler. So the feed, so Xn is a feed, right, into the partial reboiler, and the partial reboiler will produce a vapor of composition YB and a liquid with composition XB, right? And YB and XB, they are in equilibrium with each other, so they are sitting on this point on the equilibrium line. Okay, so that point, the blue circle gives you the your partial reboiler. Okay, now if you look at this XB, YB, XB is not equal to Xn. XB is actually smaller than Xn, right? So that's why partial reboiler is kind of another equilibrium stage. It can further, if you compare the bottom composition, it's slower than this Xn, which means after Xn is fed into the reboiler, you can further reduce the amount of the light K in and achieve an XB that's lower than Xn. Okay, so that's the difference. Remember, for total reboiler, your reboiler sits on the 45-degree line. For partial reboiler, your reboiler sits on the equilibrium line. Okay. So similarly, for the condenser, there's also the difference between total condenser and partial condenser. In the total condenser, all the vapor is condensed back to liquid. Okay, so then your distillate will have the same composition as your liquid coming back to your column. And for your partial condenser, only a part of the vapor is condensed. So the condenser will produce a mixture of liquid and vapor, and the liquid will be returned back to the column as a reflux, whereas the distillate and the vapor will be discharged as a distillate, which is a vapor. And this is also another equilibrium stage. Okay, so next let's look at an example in which we use that involves a partial reboiler and partial condenser. Okay, so we have a feed of hexane and octane entering a distillation column that has a partial reboiler, one equilibrium plate, and one partial condenser, right? The feed is a bubble point liquid that's fed to the reboiler, right? So reboiler is at the bottom of the tower. So in this case, it's fed into a reboiler. That means we do not have a stripping section. Then bubble point reflux from the partial condenser, right? Because it's a partial condenser, it's going to produce a bubble point liquid as a reflux, and also a dew point vapor as the distillate, right? So the vapor distillate contains 80% of hexane. We have a reflux ratio of L over D is 2. Assume the partial reboiler plate and partial condensers are all equilibrium stages. Now we need to use the McCabe-Celi method to calculate the bottom composition and the distillate. Okay. So to solve this problem, let's think about some problems, some questions first. First, how many equilibrium stages are there? Right? We have one equilibrium plate, right? But in this case, we have a partial reboiler that functions as an equilibrium stage, a partial condenser that also functions as an equilibrium stage. So we actually have 3 equilibrium stages. What about the operating lines, right? Because we have the feed fed into the reboiler, that means we do not have the stripping section. We only have the rectifying section. So we'll have only one operating line. What about Q line? So since in this case, the feed is a bubble point liquid, right? If you recall, the Q line slope is dependent on the feed composition, feed and feed condition. Depends on the feed condition. In this case, if it's a bubble point liquid, then the Q line is going to be a vertical line. Okay. Now, to answer this question, let's look at the structure of this distillation column, right? So we have 3 stages: partial condenser, plate 1, partial reboiler. We feed the feed into the partial reboiler. Okay, we know the composition of the distillate and also the LD ratio. Now we need to compute the composition of the bottom and the flow rate. Okay. So to get this, we know actually if we know the composition of the bottom, then we can compute the B and D. Okay. And in this case, we can just we can draw the operating line, then we can draw the operating line, then we can do the step off because we know the composition of distillate, right? So then we can find out the composition of the bottom. So here we know the ratio of L over D. This is then we can compute the ratio of R over R plus 1. That's L over V, which is 2/3, right? So we can plot the operating line on the XY diagram. Starting from the distillate composition, we draw a line with a slope of 2/3. Then you can do the step off, right? So that will hit after. So we have 3 stages. We can only draw 3 horizontal lines, 1, 2, 3, and at the stage 3, we're gonna hit on the equilibrium line, right? Recall that in this case we have a partial reboiler, so that point basically gave us the composition of the partial reboiler, right? So it gave us the composition of the vapor and the liquid leaving the partial reboiler, right? So the vapor is here leaving the partial reboiler, entering plate 1. The vapor leaving partial reboiler and enters plate 1, but the bottom leaves the partial reboiler and leaves the distillation column and become the bottom product, right? Then we can read off the composition of the bottom product. That's at this point, okay, XB, roughly 0.13. Okay, now we have XB, we have YD, right? And we have ZF. We also know in this case, XF, which is 0.3. But then we can use basically mole balance of the lactate, as well as a mole balance of the total feed. Then we can compute the the distillate and the bottom flow rate. Okay. So what if instead of feeding into partial reboiler, we feed into plate 1, right? How that's gonna change the way we solve this problem? So in this case, basically, if we feed into plate 1, then we will have a stripping section under plate 1. Okay. Then, in order to solve this problem, right, we know the operating line. We also know the Q line because we know that feed is a saturated liquid. Then we can find the intercept point P, right? But we don't know the basically XP. We don't know the bottom composition, so we don't know the slope of the stripping section operating line. Okay, so then you have to do trial and error. You just change the slope and do the step off, well, until eventually there's one point when you do the step off, right? Your step off vertical line will overlap with your basic stripping section operating line on the 45-degree line, right? And that gives you the ideal scenario in which you fully utilize the partial reboiler. Okay, so kind of like your partial reboiler here, the liquid stream leaving the partial reboiler has a composition of XB, and it's basically the same as the operating line composition. Let's look at how we do this. So here I'm using these two figures are the same as the previous one. I'm using them as just kind of a template to do this design. So if we have a stripping section operating line that has a slope of this, okay, then after stage 2, that corresponds to plate 1, we need to do a step off. We switched the operating line from the rectifying section operating line to the stripping section operating line. Right? Now, if you do that, you find out, okay, this line does not land on the stripping section operating line. Okay, so you will be able to so you will basically achieve a kind of separation with only 2 stages. That's not what we want, right? We want to do the separation with 3 stages. Okay, so this slope is basically too steep. This line is too steep, so we do not find this vertical line does not land on the operating line. Now, if we basically draw a operating line that's less steep, in this case, if you starting from the stage 2, draw a vertical line, it's going to land on the operating line, right? At that point, you can draw a horizontal line, then cross the equilibrium, then you can draw a vertical line again. That's gonna, cross the 45-degree line there. Right? In this case, we use these 3 stages, right? We can still achieve the desired separation, but since this point does not over that point, we really do not fully utilize, the distillation column. Okay, then you can just further reduce the slope and do this back and forth until this point overlaps with that point. Then you basically get this solution. Okay. Okay. Then from this line, you can read off the composition of your bottom XB. Then from mole balance, you can compute B and D. Okay. Okay, so we're going to stop here.